My students are always asking me what the strongest acid that I have back in the chemical stockroom is. And probably I would say the answer is concentrated sulfuric acid. Sulfuric acid comes as 18 molar. That's pretty strong. And then my students, the follow-up question is, well, what's the pH of that? Let's go ahead and try that. What is the pH of 18 molar sulfuric acid if the first Ka is large? All they say is large because sulfuric acid is a big 6 acid. It's strong. It has a huge equilibrium dissociation constant. It's essentially 100% dissociated. They also tell us that the second Ka, Ka2, is 1.2 times 10 to the minus 2. That's actually pretty big. The second dissociation, although it's not strong acid, is one of the strongest of the weak. It's pretty significant. So let's go ahead, use our data to find the pH and to calculate the concentration of the sulfate ion in solution. So let's start off with our sulfuric acid. Now, sulfuric acid, H2SO4, if you put sulfuric acid in water, it's going to dissociate 100%. But which dissociation 100%? Only the first H. The first H will 100%, one-way arrow, come off, go on to the water to make hydronium and the bisulfate ion, HSO4. Now, we're going to go ahead and do what's basically an ice table. I start out with 18 molar sulfuric acid. Now, how much of that do I lose? Not a little bit, not minus X. I'm going to lose it all. It 100% will lose that first H+. So I'm going to take away 18 here. I'm going to add 18 molar here, and I'm going to add 18 molar of bisulfate. At equilibrium, the bisulfate will be 18 molar, the H3O plus will be 18 molar, and I will have no undissociated sulfuric acid. That's what I have at equilibrium. Now, if I want the pH, if there is a very large difference between Ka1, large, and Ka2, 1.2 times 10 to the minus 2, we can say that all of the significant H3O plus ions comes from that first dissociation. We can use the first dissociation to find our pH. Let's go ahead and do that. The pH of 18 molar sulfuric acid is negative log of 18.0. That gives me a pH of negative 1.26. A negative pH? Yep, you can have a negative pH. So there is the answer for part 1. Now part B says, let's find the concentration of the sulfate ion. In order to find the sulfate ion, we need to let bisulfate ionize one more time. And we need to lose that second H+. That's where the Ka2 is going to come into play. So we'll take HSO4 minus. We're going to put it in water. It's going to lose the second H+ to give us some more hydronium. And there's the sulfate that we want. Let's go ahead. We put it in water. Let's make our ice table. The initial value of the HSO4, well, that was from above, 18 molar, 18.0. Now, we have one of these already. We know that from the first dissociation, we have a lot of hydronium in the water, 18 molar. So this originally is at 18. We don't have any sulfate before the second dissociation. That one's set at 0. So we're going to move in the forward direction, take away X, add X, add X. At equilibrium, the sulfate ion is going to be X. The hydronium We're going to rule of 100 that 100 times this is less than 18. The hydronium is, as we said, 18 molar, and the bisulfate ion is also 18 molar if we rule of 100 that. Now, we have our equilibrium values. Let's use the second Ka, 1.2 times 10 to the minus 2. Ka2, which is 1.2 times 10 to the minus 2. That value, 1.2 times 10 to the minus 2, is going to equal x times 18, all divided by 18. Your 18s are going to go ahead, cancel out, and that leaves you with x, or the concentration of your SO4 2- equal to the second dissociation constant, 1.2 times 10 to the minus 2 molar. So there you have it. There's the pH of concentrated sulfuric acid and the sulfate ion concentration. Take care.